Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and in this video, I'm going to talk about energy and power in AC circuits. We will begin with a couple of definitions. We can define energy to be the limit as t approaches infinity from minus t over 2 to t over 2 of the magnitude of x of t squared dt, where t is the period. And then the units for energy will be in joules, which we abbreviate as J. Power can similarly be defined as the limit as t approaches infinity of 1 over t times the integral from minus t over 2 to t over 2, x of t magnitude squared dt, and the units will be joules per second, which is watts. So those were some values that will be useful to us in the future. But I want to also give you another sense of another way of measuring voltage and power and current, and that's what we will call RMS. But let me kind of give you an explanation of why. So think back to how a resistor works. We have the power consumed by a resistor is equal to the voltage across the resistor times the current through the resistor. So P is equal to VI. And using Ohm's law, we can rewrite that to be power is equal to V squared over R, or it's also equal to I squared times R. If we consider V of t to be a sinusoid at a frequency omega with amplitude A and phase angle phi, then we can write the current as A over R cosine omega t plus phi. So in other words, we just take the voltage and divide it by the resistance. Using our equation for power, we can then write the instantaneous power, P of t, will be equal to A squared cosine squared of omega t plus phi divided by R. We can go ahead and rewrite that as A squared cosine squared of omega t plus phi over R squared times R. And the reason we want to do that is just to get it in a slightly different format. We can then rewrite the average power as 1 over R times 1 over t, the integral from 0 to t of A squared cosine squared omega t plus phi dt, which will be equal to 1 over R times A squared over 2. From this, we can get our definition called root mean square, which is RMS. And so this is just a way to relate the generic magnitude of x squared, magnitude of x of t squared, where x of t is either a voltage or a current, and so we can define the RMS voltage. VRMS will be equal to the magnitude of the voltage over the square root of 2, where the magnitude of the voltage is A. And similarly, we can write IRMS as 1 over R times VRMS, which will give us 1 over R times A, that same magnitude, over the square root of 2. Now, to get the average power, we can just say P is equal to VRMS times IRMS, which will give us equal to 1 over R times A squared over 2. So that works very well for resistance, but what happens when our impedance is complex in the case of an inductor or capacitor? The phase of the current and the voltage are not the same in either the case of the capacitor or in the inductor. So for the inductor, we can, for example, write I of t is equal to A cosine omega t plus phi for a sinusoidal current. Then we can write V of t, which is equal to L di of t dt. And so that gives us a voltage, which when we take the derivative of the current with respect to time and add in the multiplication by L, the voltage will be equal to minus A times L times omega sine of omega t plus phi. And so if we multiply the voltage times the current, we get the instantaneous power, which will be minus A squared L omega cosine omega t plus phi times sine omega t plus phi. And from this we can actually tell that when we compute the average power, 1 over t, integral of 0 to t of p of t, where t is the period, we end up with an average power of 0. So for a capacitor, you still have an instantaneous power that is a cosine times a sine, but it will also have an average power of 0. So this is an important fact. Capacitors and inductors do not consume real average power. They do both have an instantaneous power that can be computed.